Hello students, in this video we'll see an example of a non-orientable surface called the Mobius band. So let's consider a unit line segment let's call it L, positioned so that its midpoint is at 1, 0, 0. And so let's draw the XYZ plane. There's the Z-axis, there's the Y-axis, there is the X-axis. And so over here at the point 1, 0, 0 is going to be the midpoint of this line L. So it looks like this. So that's 1/2 over there, and that's 1/2 over there. That's my line L. And now what I'm going to do is I'm going to take L. If I was to rotate L around the unit circle, so let's look at the unit circle over here. So there's my unit circle. That is x squared plus y squared is equal to 1. And so what we can do is we can say L has parameterization. I can write it like this. I can write it as 1, 0, and then t, where t goes between -1/2 and 1/2, right? So -1/2 less than or equal to t less than or equal to 1/2. That means it's a unit line segment. Now, if I was to rotate L around the unit circle, I would get a cylinder, right? So one thing we can do, so if we rotate L around the circle, around the unit circle, and if we did that, what do we have? We'd have this sort of a situation. We'd have a cosine of theta, then a sine of theta, then a t, and the theta goes between 0 and 2 pi, right? So here theta goes between 0 and 2 pi. And so that's what I would get if I was to take my line and just straight up rotate it around this circle over here. And I get a cylinder this way, right? And so this would form a cylinder. Okay? But now we're going to throw in an extra catch. The catch is the following. As we rotate this line segment about an angle of theta, so if this is the angle theta over here, so if we rotate L around unit circle with angle theta, and then we're going to rotate L about its midpoint parallel to the z-axis an angle of theta over 2, right? And then rotate L about its midpoint by an angle of theta over 2. And now let's figure out what this sort of the surface to look like. So we can imagine what's going to happen over here. So I'm taking this line segment L and I'm moving it, and as I move an angle of theta, I've rotated the line segment half of theta parallel to this z-axis over here, okay? And so let's draw the configuration and see what that's going to look like. So by the time I have rotated by an angle of theta, if that's my angle theta over there, the line segment L now looks like this. That was the original line segment. And this angle over here is theta over 2, right? And so if that angle over there is theta over 2, we can draw this thing over here like so. And then this angle over here is going to be theta over 2, like that. And then if I parameterize this line segment over here as a unit line segment by t, remember we're parameterizing the line segment by t over here, then this length over here, if I draw a length of t, the length of t over here, we can also say that there's going to be a theta over 2 over there, and we get these configurations. And now this side length over here, so that's also going to be theta over 2, right over there. And so what are these side lengths? This horizontal side length over here is going to be what? It's going to be t sine of theta over 2. And then this length over here is going to be t cosine of theta over 2, like that. And so what's going to happen now is I'm altering. Now I don't have this cylinder parameterization, but I'm going to subtract off something from the x component. How much am I going to subtract off from the x component? I'm going to subtract off this quantity over here from the x component, and then this quantity over here from the y component over here. So both of these things over here, so this quantity over here is going to be subtracting both the x and the y components, and this component over here is affecting the z. So I'm going to modulate the z by this parameter over here. And so we get this parameterization r of u, and we can say, let's say theta and let's do theta and t now. So let's do r of theta and t. R of theta and t is going to be what? R of theta and t. is going to be, well, how much are the x and the y changing? It's going to be cosine of theta, but how much is the height changing by? It's changing by 1 minus t and then sine of theta over 2, like that. And that's hit with a cosine of theta. And then we're going to have a 1 minus t sine theta over 2. That's hit with a sine of theta. And then finally a t cosine of theta over 2 over here. And with this parameterized, of course, t goes between -1/2 and 1/2. So of course, -1/2 less than or equal to t less than or equal to 1/2. And then what? And then we're going to do a, what? And then theta goes between 0 and 2 pi. Like that. Great. And so this parameterizes the Mobius strip. So this is a parameterization. This is a parameterization of the Mobius band. Okay. And you've probably seen Mobius bands in some of your earlier math classes. The idea behind a Mobius band is the following. What you could do is you can take a rectangular strip of paper like so. Imagine this rectangular strip of paper like this. If this is my point over here, A, and this is my point B, and this is my point C and my point D, to construct a Mobius strip, what you do is you fold A onto D, so fold A to D, and fold B to C, and glue. Okay? And so what you're going to get is you're going to basically induce a half turn on this rectangular sheet of paper, right? And the cool thing about this is that this Mobius band is an example of something that's not orientable, right? So this is not an orientable surface. So proposition, the Mobius strip, let's call this strip over here M. So M is not orientable. And that means there's no way to choose the normal vector in a way that's consistent with the parameterization. In other words, the normal vector might change signs as you go from one direction to another. And we can exactly see what's going to happen over here. So what I want to do is I want to compute partial r, partial theta. So let's do this. Let's compute partial r, partial theta when t is equal to 0. So in other words, at a point theta, comma, 0 for t, right? So that's going to be 0 for t. That's along what? That's going to be along this sort of this medial circle on the Mobius band, okay? And so what's going to happen over here, if we do a theta derivative of this thing and plug in t equals 0, what's going to happen? Well, of course, if we do a theta derivative of this, we're going to have what? We're just going to, if we do a theta derivative of this thing over here, right, and plug in t equals 0, what's going to happen over there is those terms are going to go away, right? If I do a theta derivative of this thing over here, I'm just going to get a negative sine of theta, right? So that's just going to be a negative sine of theta, right? And let's make sure we understand that, because the derivative of cosine with respect to theta is going to be negative sine, and then the derivative of this mess is going to have something that has a t in it, but when we plug in t equals 0, it's going to vanish, right? The same thing happens over here. So when we look at these terms over here, when you do a theta derivative of these things, you're going to do the theta derivative of sine, which is going to be a cosine of theta, right? And then what? And then you're going to do a theta derivative of this thing and plug in t equals 0, then you're going to get nothing over here, right? So you're going to get a 0 over here. So that's what we're going to get for the r, the derivative of r with respect to theta when t is equal to 0. If I do partial r, partial t, and then plug in theta and then plug in 0, well, if we do a t derivative of this thing over here, what are we going to get? If we do a t derivative of this thing, we're going to get a negative sine of theta over 2, cosine of theta over 2, right? So that's, and we plug in t equals 0. And when we plug in, there's no t derivative over here, so we're going to get a negative sine of theta over 2, cosine of theta, and then what? And then we're going to have a, over here, we're going to have a negative sine of theta over 2, sine of theta, like that. You do t derivative, and then finally you do t derivative of this, and you're going to have a cosine of theta over 2, like so. Okay? Excellent. All right, and so now, of course, what we're going to do is we're going to do the cross product of these things and see what's going to happen over here, right? So let's do the cross product of these things. So then my n hat of theta and then 0 is going to be the cross product of these two things. And so let's do it. We're going to cross these things. Take the normal vector. Like that. Good. And so let's think of what's going to happen. So I do the I component. We're going to have a cosine of theta over 2, cosine of theta over 2 for that first entry. And then the j entry is going to be what? The j entry is going to be, we're going to punch out these two things over here. So this is going to be a sine of theta times cosine of theta, and that's going to be a negative. So I'm going to have a sine of theta, a cosine of theta over 2, right? And then of course that was it. And then finally what we're going to have in the last entry is not going to matter so much over here. We're going to have a negative, we're going to have a positive sine squared, then a positive cosine squared. So the last entry is just going to be a sine squared of theta, sine of theta over 2. Like that, okay? Now here's the kicker over here. As theta goes to 0, so in other words, the limit as theta goes to 0, like this, of what? Of n hat, from the positive side, of course, right? N hat of theta and 0 is just going to be what? Well, this is going to be a 1, that's going to be a 1, that's going to be a 0, that's going to be a 0 over here. So we're just going to get a 1, 0, 0. But if I look at the limit as theta goes to 2 pi, which is the same angle as 0 from the left, of n hat of theta and 0, what's going to happen? Well, what's this going to be? As we go to pi over 2, this becomes a 1, this becomes a cosine pi, which is negative 1, then a 0, then a 0. And so this is not equal to negative 1, 0, 0, which is negative I hat. So in other words, on this strip, as you approach the 0 angle along this median circle over here for the Mobius strip, what's happening? Along the median circle of the Mobius strip, what's happening is you start over here. If you do the normal vector in this direction, you're in the direction of I hat, so you're in this direction over here, like so. But when you come over here in this direction, you're getting a normal direction that's looking like this over here. So in other words, the normal vector over here, that's n hat and that's n hat from different directions, and the normal vector is changing orientation, right? So the orientation is flipped, orientation flips for the normal vector over here. And when the orientation flips, that means the surface is non-orientable. Now, this may not seem like a very important issue over here, but it plays an essential role when you're trying to prove the vector calculus theorems like Stokes' theorem, for example. Stokes' theorem assumes that the surface is orientable, right? In other words, because when you're doing a flux integral, you have a dot n hat. In order to use any continuity arguments when you're proving vector calculus results, you need to assume there's a consistent way of choosing the normal vector in order to make your continuity arguments work. In other words, you don't want to have a jump discontinuity in the direction of the normal vector because that will destroy the orientation, and that will make all the results about the cancellation and the Riemann sums of these results completely false. So this idea of orientability is important, and this is a prototypical example, easy to construct, right? You need to take a sheet of paper and do this procedure which I told you about. Take a sheet of paper, rectangular sheet of paper, fold A and D together, fold B and C together, and that's going to be a Mobius strip. And you can actually sort of put a little, maybe like a toothpick on that surface and just sort of see as it moves around how the orientation flips along the medial circle, and that proves the non-orientability of this Mobius band. Thank you very much.